one. It's depending on the streams, but where is PowerPoint? Okay. Okay, so we're talking about collisions, and in particular, we want to go over what detection is, determination, response is. So can anybody tell me what detection is all about? What is detection? What did you learn this last week about detection? Did something it, right? We're asking the question, did it happen? Okay?
Saying it was a boundary condition passed. But if there's some condition that we don't want to be,
right,
was violated, it is, we do something about it.
Yes. Okay. So, did it happen? Okay, determination. What's determination? Collision determination.
Figuring out where and how to hit the object.
Where and how to hit the object. All right. And response. What's response all about?
What do you want to do afterwards?
What do you want to do afterwards? What are some things we might want to do afterwards?
Reset the position back to where it should not have gone past.
Sure.
Change velocity vector, reduce hit points, lead object.
Yeah. All different kinds of stuff.
Initiate explosion simulation.
Start other events. Yeah, that's good. Let's see. What else was I asking? Anybody try modeling the effect of a service on it?
I did that, but I could have the paper I can
Right. And did anybody remember what force diagrams look like? Bunch of arrows. Those really come in handy when you're trying to do all this work, because it's easy to forget something, So putting that force diagram helps you think about the problem. Because as soon as you start doing like collisions or things like that, then you're thinking, well, if we had an object on an incline, how would I do that? Like, what data structure am I going to use? How am I going to represent this object on an incline? That's not as easily done as you might think. And then, of course, how do you determine vertical and horizontal acceleration? And the reason I say it's difficult is because you're like, well, what object am I talking about? Am I talking about a sphere? Am I talking about a brick? A rectangle? Am I talking about a polygon object? The polygon object can be more difficult than the other two cases. Because what if one vertex is touching and then the other ones are just slightly like hovering above? What is that like torque going to do? We might want to have stopping conditions, right? Okay, so that was the purpose of that, of those questions, to get us to think about how much work can be involved with collisions. Did anybody watch the circle versus circle collision video? I watched it. It's one of those things I felt like it sucks you in. Like, this looks like a long video, and you start watching it, and you're like, no, I want to keep watching. They actually has more videos on that. Anybody watch extra videos? No. Depends on what you're looking for, but so I put that in there if you're looking for some more particulars on how you might do something. You did a good job explaining that. Okay, so what do you think is meant by a posteriori or a priori? Post and prior? Yeah. What does that mean, like, from a practical standpoint? It's tricky. Which one do you think is easier to do? I think posteriori is easier. I think it's easier than the other one. Why do you think I think it's easier?
Try both.
Why do we think we know something it already? Like, what if you're about to things about this kind of stuff goes like that, nothing happens. That, like, it's like, oh, that's gonna happen.
I mean, the thing is if you figure out if they collided, you've kind of already done the calculation to like update the system anyways. It's there. Like, you already have that information. You know, like, you could do it again or something, I suppose. And also, like, figuring out a lot of like the results of which are a lot easier once you like, oh, this is the situation. If the collision didn't happen, then let's just perform some corrections to put it in the right place. So at least that's what I was getting at it.
Okay. So this discrete or continuous is kind of talking about the difference between a posteriori and a priori. In other words, you're going to know in advance or you're going to know after the fact. Now, here's why I think a posteriori is easier to do. Because all this time we've been talking about using this time step to move the simulation along. Okay? And a posteriori kind of works in that same mindset of, so to draw it on the board, this is the difference between a posteriori and a priori. So let's just say we have a boundary, okay, and we have an object moving in this direction. Okay, so you calculate the next time step, and you calculate the next time step, and you keep doing this, stepping along, and every time you're checking for collision with the barrier. Okay, and let's just assume we have a fixed velocity here. In other words, so over here, now we got our collision. Okay, and so all we have to do is check the collision, check the collision, check the collision, check the collision, check the collision. And if it happened, then you deal with it. Now here's how a priori would more likely be implemented. We have a barrier. We have the same object moving in this direction. So now we need to see, based on the characteristics of the way this object is moving, where is it going to be on the next frame? Okay. So we say that it's going to be traveling along this line, say to this line. And so what we need to do is then see, does this intersect with the object or not? Which it doesn't in this case. Okay. And then does it intersect again? You repeat this process, but here's why I think it's more complicated to do it that way. Because now you're trying to, this one we can just do our box versus box. We can just check to see if it happened or not. And this one, now we have to kind of add a new type of primitive to test whether this is going to intersect that box or not. So I think this is more complicated to implement. I think it can be more accurate, but I think it can be more complicated. Where a posteriori breaks down is when you have like two objects and they're both moving. So let's say we have object A moving in that direction. Okay. You have object B moving in this direction. And if your time step is too small, then suddenly this guy is over here, and this guy is over here, and then it's like no collision happened, even though clearly it did. But if you use the appropriate time step, then you could avoid that happening. Okay? And it's just a matter of adjusting the time steps. Whereas the continuous one, I think it makes the process more complex. There's a little bit more moving parts with this one. It may be, and think about this. How are you going to do this with like a rigged human being? How is that going to work? Now you're animating, Now you're trying to do this A priority. Now, you tell me which one do you want to implement? Which one would you rather do now? This one A priority or A posteriori? Because there's so many, like this movement is like dependent on this movement. And so yes, that's this is why I think A posteriori is more easily implemented. Now if all you're dealing with is these simple examples, then maybe it seems like, oh, this would be the way to go. It doesn't seem like that much extra work. But then when you're dealing with like a lot of constraints, then all of a sudden it seems to make more sense to, maybe in some cases you have to have a special, or actually what you could do, use A posteriori to detect when it happened, and then you switch to this approach to do the determination. Where did it happen? Okay, so sometimes you use the two approaches together, but more generically, you use this one because it's easier to implement a system like this. Okay, optimization. So, what's the if we have to give a big O number here? How would we characterize collision detection?
I mean, it's due to multiple frame. If we're doing a posterior style.
Okay.
So, the calculation for it is, but it's every object with every object. If you're being the laziest one ever, right? Which is
N squared. Yeah. Okay. So by itself, I mean, maybe N squared is not so bad. It depends on what your worst case scenario is, right? Is every N squared algorithm terrible?
Not for 10 objects.
Not for 10 objects, right? I mean, so if you're only dealing with a limited number of objects, then maybe it doesn't matter. Okay, on the other hand, so optimization. So collision detection is something that's, we often would like to do something about. So how do you think maybe we could optimize? How can we what are some methods we could do to get rid of that N squared? Turn that N squared number to something else.
Don't do collisions for objects that are not even remotely close to each other.
Okay. That requires at least one O(n) squared effort to determine. I would think.
You can sort of do the box thing, where again, you box things, you grid things up in advance.
Right.
And then
It's kind of like using a hash table. Just only check the hash where the collisions are, or you only have to check the collisions where the hash kind of doubles them up. Okay, so it's like the hash table algorithm in a way. So, I think the ultimate goal is to try to get it down to O(n) if you can. Right, that would be nice to do.
that's for each object.
Well, I mean, if you only have objects that are close to each other, on average of like 1 to 1, then you could get it down to O(n), right? And maybe you have it less than that. If it's seldom ever that objects are close to each other, you don't need to check the collisions. So, but I would say if you have a reason, that you could get the number down, but it's still going to be variable. It could end up being worst case an O(n) squared algorithm. So.
Question about the discrete continuous. Can you hybridize those? Like, is that a thing that's done?
What's that?
The discrete continuous methods. Can you hybridize those? Can you be like, we're doing discrete with our bounding boxes, but once we pass the bounding boxes, we're doing continuous definition?
Well, that's kind of what I was mentioning over here, that maybe you want to use A posteriori to do the rough detection, and then use A priority to do the determination, where you slow up the time step or do whatever you need to find out where did it happen. Okay, but it's important to make sure this has enough resolution that, hypothetically speaking, this box doesn't fit here, and then now we have something on the other side. Okay. And then There's a notorious example out there of big rigs over the road racing, but I only think 2 in this class have not seen it yet. Are you familiar with this one?
No.
Okay.
It's entertaining to watch it.
It's very entertaining. Okay. So let me find a.
Less than what can go wrong.
Yeah, this is.
Yeah. Human civilization is peak.
Okay.
Big Rigs Over the Road Racing is one of, if not the, best video game ever made. Not just the best racing game, not just the best PC game, the best video game ever made. First of all, the graphics are amazing. A lot of times I felt like I was like in the real world. Like this is a virtual reality machine that I stepped into. Because everything looks absolutely stunning. And if you put your graphics on the highest setting, it's really gonna feel like real life. Like, you'll be playing the game, and once you take your eyes off the computer screen, you'll think you're still in the game, because the graphics of real life and this game look exactly the same. Look at that grass. I mean, that's exactly what grass looks like after a rainy spring day. Just dew all over it, flashing in the beautiful sunlight. God, a lot of times I won't even actually race. I'll just drive through the levels and just look at the pastoral scenery. This game isn't so much a game as an experience, a wonderful experience. An experience of pure euphoria. Now, my game didn't come with sound effects or music. I'm not sure if they're supposed to be in the game, but I think that's so fantastic. Because a lot of games have really annoying good music and sound effects, and that really takes the focus of the gameplay. You know, when you're playing a game, you need to focus on what's important, the gameplay. When you're focusing on trivial things like story or music or sound effects, it's gonna take you out of the gameplay, and you're not gonna appreciate the gameplay as much. Now, one of the greatest things about Big Rigs Over the Road Racing, what really makes the game stand out from other racing games, is the versatility of your truck. Your trucks aren't just little weak, worthless trucks that have to follow the road and they veer off the road. They're gonna drive like crap. Your truck drives the same everywhere. You can drive through buildings, through lampposts. You can drive up mountains and not slow down even an ounce. It's absolutely fantastic. And there's just so many different trucks and environments for you to play through. This game has a collection of over 4 different playable trucks. That's right, 4. Big Rigs also has a ton of different levels, like Devil Passage 1, Devil Passage 2, Forgotten Road 1, Night Ride, and of course the fan favorite Small Town Road. You have to be careful though, because a lot of these maps do not actually work, and if you pick a map that doesn't work, your game will crash. Possibly one of the greatest things about this game is the competition AI. You see, you're actually racing against other trucks. In most levels, there's one other truck you're racing against. And the thing is, when the race starts, that truck just stands still. And you can literally go all the way around the racetrack. You can literally finish the race, and that truck will continue to just stand there. Now, I know what you're thinking. Well, how's that good AI? It's social commentary on racing. It's basically saying, what's the point of racing? Just enjoy the beautiful scenery. I'm not gonna race you. What's the point of competition when we have these beautiful pastoral settings for you to just stroll through and enjoy? Look at those trees. Also, the bridges don't work. When you actually drive onto a bridge, you drive right through it. Some people might think this is a bad thing, but the fact is, you don't need bridges. Like I said, your truck is so amazing, it can drive anywhere and it won't slow down. There's no friction going down hills, going up mountains, going through buildings and trees. nothing stops your truck. You can literally drive off into the netherworld and your truck will be fine. It's really durable.
So we'll stop it. We'll stop it right there. You can finish watching it.
You know, it's been almost 10 years since this fantastic game was made. It was first developed in 2003. And I think it has really stood the test of time. You know, a lot of games, older games, 10, 20-year-old games, they just can't keep up with the graphics of today. But Big Rigs actually pioneered a lot of the graphics we see today. A lot of really complex cell shading and things like that. Big Rigs is one of the games that pushed the graphical limits of gaming and brought us to this new generation of pristine graphics. Big Rigs Over-the-Road Racing is an absolute classic. I consider it the best game ever. Some people might think it's only the best racing game or the best PC game, but I'm just going to go out and say it. It is the best game ever made. It is a pure, unwavering, solid 10 out of 10. There is nothing wrong with this game. It is perfect. It is the ruler by which other games should be measured. Thanks for watching. Goodbye, my friends.
Yes, that's a pleasure for Planet.
Be very wary of your game is measured against.
Okay, so that is a great example and a very hilarious example of what happens when you don't do collision detection or you do it badly, right? Because you're doing collision detection with the ground, but it's just more or less what direction is the face going, right?
Yeah, it's literally locked to the ground. If you're there were times like that should jump.
Yes.
Nope.
Okay, so yes.
Is there a chance at some point today you could maybe go over the homework?
Oh, yes. Yeah, we can go over that. Okay, so collision determination. Okay, where did the collision happen? Now, do you think that there are some difficult cases here? Like, let's kind of brainstorm. What do you guys think? What would be a difficult case for collision determination?
Any non-standard polygon, I'd say.
So, non-standard polygons?
Anything that's not a cube. Well, this is me. Anything that's not a cube, sphere, or plane.
So, like, concave things with like dents inside of them, where like you can look like you're inside of an object, but you're not actually inside of it.
Okay.
Those ones are nasty, from what I've heard.
Okay, that could be difficult.
Or what if you're hitting something that's concave? You hit multiple faces at the same time.
Well, if you think about it, though, most game levels would be very uninteresting if they're only convex, and so there are ways via like binary space trees or so on that you could actually simplify that. Yes, Campbell.
These types of collision. If say a character, like say in Super Mario 64, if Mario's going too fast, then they can go outside the bounds.
Sure. Yeah, you make too big of a time step where it's you don't have proper boundary conditions, like Big Rig Over-the-Road Racing. Just drive off the world.
People have disassembled Mario 64 fairly extensively, like the watch for rolling rocks. Yeah. Have you seen that one?
I don't think I've seen Watch for Rolling Rocks. That might be. That's could be good. That's a we're talking about. So it's a.
There was a split.
Watch for rolling rocks.
I feel like
0.5. It's kind of a long one, so you probably not watch the whole thing. It's like this concept. So the 0.5 A presses is the point. So this guy, he tries to do Mario 64 by with his little A press, so without hitting the jump button. And he does these things for, like he's trying to get up a ledge that you can just easily jump up, but instead he, okay, now I need to build up speed for 12 hours, as he like.
In this video, I'll be explaining exactly what.
And just builds up. He like talks about parallel universes in this video, and all sorts of other stuff about some weird characteristics with converting from floating to decimal that happens to, but.
So this could be a good research project.
It's a good watch.
Okay. I have to put this on later. just to kind of appreciate the problem. But
at least watch it. It's kind of long class, but
yes, okay.
like if you go to an entirely different level to save certain memory states for the game.
Oh, I would say that's pretty well deconstructed. Yes, yeah,
like
that's funny.
He clones entities to make a bridge out of Goombas to jump across, like instead of hitting the jump button.
That's funny. Yeah, so determination, yeah, that could be a difficult problem. Yeah, I'll take a look. Maybe I can find like a shorter clip to kind of show to the entire class. Make a
Shorter videos.
yeah. So I'll try and find something, or if you guys find something, put it up. Actually, this is a great opportunity. Put it on the Slack channel. Say, hey, I found it, and then everybody. That's the best place to do that. Okay, let's see a response. Okay, so this is we talked about this already. What do we do with the collision? I think I have a typo on this slide, but remember what the superscripts were represented? Right. So we do before and after, and if it's a good way of like writing down their sometimes it's, if you think about it, you have a mathematical problem that you'd like to express to somebody else, or you'd like to express your problem in a mathematical kind of way. So this is a good example of using, say, superscripts to kind of, in shorthand, mark, events happening before, events happening afterwards. It looks a little bit cleaner than saying like n+1. And what if you want to use n to talk about the normal or the tangent? So sometimes you can come up with a nice mathematical way of talking about certain concepts, and that is also something you should be looking for in your research. When you're talking about your problem, do people have a notation for talking about that particular problem? For example, in computer graphics, we have this concept of a light path. And so sometimes there's what we use is a regular expression notation for that. So we might say that if we're talking about the light from, we have a light source with a light, and we have the camera. So we might say that we hit a diffuse surface, and then we hit the light. Actually, sometimes we use V for the camera. So we might say this is a light path because we're going camera, a diffuse surface, to the light. And what if we have a specular surface? Okay, so we could say we have the camera, and then we have a specular surface or a diffuse surface. We're not limiting ourselves to that. This is a lot of regular computer graphics right here, because a lot of times you just say, okay, drawing a polygon, is this lit or not? And then is this, what is the direction of the camera? And then you have like global illumination, which says, well, if we're starting from the light, we could hit any number of specular or diffuse surfaces before we get to the camera. And now this represents any number of, you might have lights hitting a surface, bouncing off another surface, bouncing off before it gets to the camera. Okay, so sometimes you'll see different mathematical notation out there to talk about your object or to talk about your particular problem. So it's good to get familiar. Watch out for those kinds of things. This is an example of that, where I doubt in physics you ever saw pluses and minuses on your velocity vectors. But I think when you're talking about simulation, it makes a lot of sense to use that kind of notation to talk about the problem. Okay? And when you're faced with like a 2-column page layout on a research paper, it really helps to have short notation, because you don't need a formula like wrapping and looking terrible. Okay, so yeah, keep that in mind. Or there's not enough dots per inch on your printer to like represent the formula that you try to squeeze in one line. Okay, so algorithms. Okay, we talked about a couple on the hybrid topics video, sphere, and sphere plane. So Who would like to just explain how to do sphere-sphere collision?
Center to center distance. Yeah. And if you're within 2 radius, then fit.
Okay. Can anybody modify that so that they don't have to be the same? They could be different sizes?
Radius 1 plus radius 2.
Yeah, sure.
There you go. Okay. How about sphere plane?
It's distance from the point on the plane.
How do you determine what?
But from the point that's directly outwards from the plane towards the sphere.
Sure.
Like 90 degrees. That's
How do you know what the point on the plane is? I know I didn't talk about this in the video because I was going to talk about it in class, but how do you come up with that point?
if it's a sphere, it should just be the nearest point.
But you need the point on the sphere for the
That's
equation.
Calculation, but I don't remember. I just copy pasted it from the forum.
How would you do that?
And then you can use the normal on the point that represents the center of the sphere to do line intersect plane. Gives you the point.
How would you do like practical? Like how would you code this out? I'm gonna add planes to my program. Add planes to my program.
Does the point really matter? Because we were doing dot products to select only the part of the line that was in the
You have to subtract the point from the center of the sphere with the point on the plane.
Closest.
It doesn't have to be closest to the plane. It just has to be on the plane.
because the thing is, you're going to use the dot product to select only the part of it that's cast onto the normal. So
I
that's,
got you.
Yeah.
that tells you the distance.
So yeah, but how do you determine what that point is?
Think of it as beyond an axis of line of plane, but if you not, then you can't have really closer. So it's an axis of line, and you can just go ahead and take like the x, y, or z components of the sphere, whatever you need in order to line up the plane.
At that point, I mean, just pick anything you want on the plate. There's the standard one that I can't remember, whatever the.
So for this particular case, what you could do is you could just define the plane as a point and the normal it's facing. So you pick the point in advance. You just say, I'm adding a plane, and so maybe you just pick one of the points on the polygon or the triangle that the plane represents, and that is the point. And then you already know the normal, and then there you go. You got a point on the plane. So it can be any point on the plane, or you can make that part of the definition. You could just say the origin of the plane is here, and this is the direction it just happens to be pointing, and that represents your that represents your the point. So you could just use you could define it with a rectangle or a triangle, and then you could just say one of the points on the triangle is a point on the plane, and then you have the normal based off the triangle that you represented. So that's an easy way to do it. So it's one of those things where it's not quite as obvious as it seems like it should be. But yeah, that's how you would do it. Just pick up if you're creating the plane from a polygon in an object that you're trying to test against, then you could just use one of the vertices. Okay, now polygons. Anybody do some research on how you do collision detection with polygons? So now we want to get more generic, right? More general. But anybody have an idea how are we going to do polygon collision?
Polygon on polygon?
Yeah. Oh, because I mean that's where we are, right? I mean, we could use spheres or we could use planes, but chances are, if you're like if somebody's writing a fighting game or you're writing Big Rig Over the Roads Racing 2 and you're trying to fix the collision detection, and now you have polygon buildings and polygon trucks, how do you keep that from becoming a disaster?
So
Nested spheres, like in the object kind of
Sure.
subdivides it.
Yeah.
That part.
Use nested spheres, but there's a limit though. because when you collide two spheres against each other, you get that normal that's like directly. So you get this rounded. It feels like objects are round and they just like circle each other.
Convex hull.
Convex hull, that's a good one.
Well, I mean, the simple thing is that polygons are planes, or subsections of them.
Sure.
If you want to be completely insane, you just do the plane calculations for all of them and then check the subsections match. That's crazy, but that's the.
It's a good starting point.
And then you attempt to do the heuristics that make it so you don't have to do it for every single polygon in your 10 billion polygon system.
It's a complex thing. Now, I mean, if you were in the earlier class, we're talking about ray tracing. So at this point, we're starting to get in the concept of like, oh, okay, we're intersecting rays and different objects, spheres, planes. We want to get to polygons. So one particular kind of intersection that you should be familiar with is triangle-triangle intersection. Two triangles intersect with each other. And one of the ways to do that is with barycentric coordinates. Okay, barycentric coordinates. But I did want to spend a few minutes talking about these two other algorithms, and they use the idea of a support function. So, anybody ever heard of a support function before? How do they work? What's the idea behind them? Sometimes they're called support mappings. Maybe I should have wrote support mappings in there. Let's think about let's break it down definition. What do you think I mean by the word support?
Helps something get done. Like it's a useful additional part that
makes
it work.
Are they functions for like specific functions like in specific edge cases types of collision?
Not exactly.
Or just regions, like with robotics, we have that flow, or like basically use that to determine where a robot can move based on like all the like you have a given area, all the obstacles in it, what axes like the robot can move on it, turn and stuff like that. Generate essentially a 3D mesh of travelable locations with Minkowski.
Okay. So it's kind of funny. The word support. First thing you think of. First word you're thinking of. Helping. That's kind of what I thought. Okay. Let's see if we can change. Let's see if we can change that around. What are these? A bridge support. So,
just triangles.
Does this change what we're thinking about support mapping? Is it really helping anything, or is it support in the idea of like a bridge? Where you might have a bridge support where it's doing a structural component.
So it's making a bunch of triangles, and we know how to do collision with triangles.
Sure, but what I'm trying to get to though is a lot of times you think of the word support, and maybe it's because we hear support like, "Oh, do you need help? Please call the support line," or and we're not thinking of. So when we see a thing like support function or support mapping, we're not thinking of what is the spot where this, there's a structural geometric component to it, right?
Wow. Again, because that to me just says the thing that helps hold things up.
Like talking spatially.
It's a different concept. It's a little bit different concept. Like a bridge support, like it is. It's not the same thing as a process. Like one is more of a process and one is more of a phenomenon. If that makes sense.
Is there another word that means roughly the same thing in standard English that would be appropriate? Like there's some synonyms here.
Let's find out. I'm the nomenclature though is a support mapping.
Yeah.
Okay.
I'm just trying to.
Bearing the weight, right? Okay, is different than giving assistance to, or suggesting truth, or allowing use of operation of something else. There's several different concepts, but I think that when we think of supporting, we don't necessarily think of this initially, right? The dome was supported by 100 white columns. So the idea behind a support mapping is you're not thinking of, initially you think, oh, how is it working? It's not working by being a helper function. It's being there to say where is the where is the actual physical force is being sustained. Okay, so the idea here is that you might have two objects, and what you're trying to do is use this concept of sign distance, like how far out am I from another object? Okay, how far away? So, we have maybe a 2D example. We have this edge here, or this point here, and we have this edge here. And so the support mapping would say, well, how far are you outside or inside? Okay, what we're trying to do is maybe you have a more complex object. Like, let's say this is not just a triangle, but this is a more like a trapezoid, okay? And so we might say, where is the support mapping from this triangle over here? And we would say that this is outside. This support mapping says that this point we're testing is outside of this object, okay? So this could be a support for this, potentially. Or not. This one is outside, so if we do sign distance from this polygon, we'll see that we're outside there. And so we say this one could be a support on this one. In other words, if we were to like resolve this system, maybe we have this case right here. We're trying to find this case. Where on this object are these supporting each other at? Okay. In fact, that's how the Gilbert, Johnson, Kurethe, or Minkowski portal refinement work. It's a matter of breaking an object into simpler objects and then finding out, am I inside or am I outside? And you basically just work your way to figure out ultimately what are the two basic objects that are colliding with each other, and then that way you can resolve that collision. Okay. So when we talk about a support map or a support function, we're talking about, okay, where on the object would we expect that physical support to be at? And that's what we're trying to do, is resolve where it would be, because we don't know where it is. So if you had two objects, let's say you had the bridge, but all you had was, you knew this line here and this line here. You would want to find out, well, where are the support functions? Where is the support happening at? So that's what we want to think about. Where is the support happening at? Because we don't know it until we've actually calculated it. Okay? It's one thing to draw it out, but if all you have is a list, then you need to find out where is it occurring. Okay? And the support maps give you whether you're inside or outside and how much are you inside or outside. Okay. Implementation. Okay, so we saw a little bit of the implementation already. But we had the windy, collision-y tumbleweeds, as I was calling them. And I can go ahead and just randomly set the size. And so their size determines their mass, and their mass in turn affects their momentum. So if you have wind in a certain direction, you'll notice that the small ones will respond very quickly to a change in wind. For the longest time, I've been trying to get one of these small ones to go underneath the big one. Not quite. They do collision detection with all of them. Yeah. It's kind of funny when you do collision, but you don't do it quite right. Sometimes what'll happen is they'll look like they're getting these rapid, like, cartoon fights. They're like switching places like crazy. Okay, so let's take a look at this from a code standpoint, and then we'll talk about the homework. Okay, so example 7. Okay, so basically all I did was I took the state vector and I just wanted to add some density to it and the radius and the mass, which I just made a function of density. I wonder if I update that every time. I don't remember if I do or not. I'll have to take a look at that. Okay, so detect collision. So this just says, did it happen or not? And all I do is I just check the distance from our x and the other x, and I just add the total radius like we already talked about in class today. A move by function. So if we have a collision between two spheres, we need to move them out. I just move them out in an equivalent direction both ways. Okay, and then sometimes we need to find out, well, what's the direction from one object to another, and we want that to be normalized so that we can use it to scale by. And then distance 2 is just returns how much distance minus the radius. So in other words, how much, if we had two spheres like this, then what does this distance be between the two? Okay, so then in the simulation, we can control the drag, and we have a new function called detect collisions, and what this does is this just goes n squared, just checks from I to the number of objects, and then we just skip it if it's the same object, and then we make sure that we're not double checking objects. So then if we detect a collision, then we respond to the collision, and the way we respond to the collision is just simply by moving them apart so they're touching. And that will resolve this collision detection. Okay. At this point, I don't change the velocities. I don't do anything like that. This would be something you could do with what we talked about, looking at the friction between the two objects and determining, is this the ground? Is this another tumbleweed? Is this another kind of object? So that would be, we'll be looking at that in the future. And then we looked at our update function last week where we just, now we're just kind of updating the wind vector to reflect what our little slidey control is. And this is all the same thing, except at the very end, we check for collisions. So we just kind of added an additional step, but it's all kind of modular, right? It's just we couldn't add an additional component to each one. Now, I will say that, I guess I mentioned this in the previous class, but I did add a few HTML controls or different functions to kind of easily add rows of controls on there. So if we want to add parameters, it's easier to do that. So there's a model of how to do that in here. And I added a function in the library to create a spiral because I wanted to make the tumbleweed looking thing. Okay, any questions on, I would encourage you guys to look at the source code for this, maybe change it, modify it. Can we add friction to it? Which we're currently not adding friction to it as of yet, but we did basically add some collision detection to it. So collision response is one of the next things that we could do.
When will you be pushing this?
So I guess technically this is already pushed, but it's on the libxor project site. So what I'm going to do is I'm going to add a link to that GitHub repository on the index for the main website. Okay. In fact, I could just do that. I could probably do that now.
And then the library that's included in like in the class repos. Are you just updating that every once in a while?
Yeah. I need to copy that. I need to copy that one over. This one.
So as far as turn in, you want us to like make all our modifications, files and stuff, and like that you're using a folder and turning that in? That'd be fine.
Yeah. Yes.
Turning that folder specifically in whatever your username is.
Yeah. I would. Yeah. Do that. Now here's how I would like the homework turned in. Okay, so let me go to the first one, which is, this one might be due next week. Maybe. No, this could be done this week. Due on Sunday. This one can be done now. At first I thought it was the particle one, but this is not the particle one. So the purpose of this first homework assignment is to just get you back in the groove of doing graphics again. And so what I want you to do is render as many objects as you can. Okay, so just get practice. Just try and flood this whole thing with as many objects as you possibly can. And that way we can kind of get ready for the particles. Okay, so if you need to do points or anything like that, so we already kind of have like a pattern for doing it. You can do it completely different if you want to, or you can just copy what we have been doing in class so far and modify that, so you don't have to kind of build all that boilerplate code up. And then try and do something interesting. Okay, so I think I kind of modeled a little bit of what I think by making something interesting is. So remember at first we had, we had the popping blocks and we just kind of had a setting, sunny setting to it. And then we added wind to it. So we kind of added something to make it more interesting, but there's no interaction. You can't do anything with it. So then I, worked on this, and now we can add wind. Each case gets a little bit more interesting, right? And now this is a little bit more, tumbleweed seems more interesting than this white little blocks that don't have any particular meaning. So I would encourage you guys to, come up with a way to make your own process or do your own thing with this. Okay, so you're going to want to update. Let's see here. I'm probably going to get rid of the. I don't know if I am or not. Give me some time to think about that. But what you're going to do is inside your username, you'll go ahead and edit your homework 1.js and put all your code in there, and make a screenshot of your code, just like the previous class. And then it would be helpful if you named your zip file whatever your username is going to be. So like for me, it'd be JB Metzger. So I would name my zip file JB Metzger, and then that way I can unzip it and then copy all your stuff over. So if you ever want to make improvements to your previous code, you're just building on top of your previous work. Okay. Okay, so what I'm expecting, it's inside the homework. So if you're on the GitHub, let's go to the GitHub site real quick. So if you're on the GitHub site and you go to homeworks, and there's a link on the front for the homework worksheets, or not. This is why you test these things to make sure. Okay, so you go to the homeworks. And if you were in this one, I just don't have index file in there, but this is what I'm looking for. So an HTML file, you almost always just have to just copy the previous one and it'll auto number, and then include, if you have a vertex shader or a fragment shader, go ahead and include that, or you can just reuse the basic one that we're using so far. There's no need to have to rewrite it. Technically, you don't need. I should modify that. You don't need a small thumbnail. It can be large. It can just copy the picture. If you're using Windows, I copy it into MS Paint and crop it, and then I save it. But this is the case. Homework doesn't just come see me as far as the particular process. But most of you are familiar with how we did it with the previous graphics class, so I think most of you will be okay. And then what I'm looking for, right, is render as many objects as you can, maintain state in a single array, do something interesting with it, doesn't have to be physically based, but then talk about what you're doing in your description on your page. So over here, I have a description that says, here's what it does and here's what it's doing. So use that to talk about what you're doing. Okay, now we have a few minutes left. So does anybody have, sometimes getting started on a research project is like not knowing the direction you should go. So we can go ahead and talk about that. I'm going to stop